to the Bay Area. Yeah, just please, thank you so much again for coming.
No. Thank you so much for the invitation. It's really a pleasure to be here. Please feel free to interrupt with questions if you have any. So today I'm going to be talking about using machine learning to increase equity in healthcare and public health, which is the focus of my work at a high level. And while I do this through multiple pathways, today I'm going to focus on a particular pathway, which is improving the fairness of decision making. Why is this something we care about? Well, here are two reasons we care about it from a social equity standpoint. The one is that we know unfair decision-making contributes to social inequity in a whole bunch of different settings, from healthcare to hiring to housing, et cetera. And the second reason is that if we can identify places that people are making unfair decisions, it suggests concrete places we might intervene to make the world fair. Fair decision-making is a topic that's been on my mind a lot recently. We last year released a class actually on practical steps for building fair algorithms, trying to make algorithms make fairer decisions. This is joint work with Koei Kodama and with Jeff Leake, and it's freely available online on Coursera. I encourage you to check it out if you're interested in this area. And the class focuses on 10 basic lessons, sort of practical takeaways for people who want to build fair algorithms. You don't have to memorize all of these. There will be no quiz at the end of this lecture. But I think the reason that organizational structure seemed natural to me is that in one way or another, a lot of my work for the past approximately decade has focused on these lessons. Now, describing all of these works and lessons in full is, of course, beyond the time we have. And so today, I want to sort of summarize some high-level takeaways and then focus on some particular papers. So I think one lesson that has really become clear to me in the course of my work on algorithmic fairness is this mingled attitude of both skepticism and optimism. Because if you work in this area, it's impossible not to see all the ways that machine learning and data science algorithms can be biased. These ways are myriad, they are difficult to combat, and a lot of my work tries to combat them. At the same time, I think there's also an importance of being optimistic here, because machine learning and data science properly applied are powerful tools to support equity. The basic reason being that the world is a deeply unfair place, and machine learning and data science afford us sort of superpowers in our ability to understand and potentially combat those inequities. And so today I want to focus on a particular avenue for doing that, and in particular using new machine learning and data science methods in order to quantify disparities in policing. Now, policing, it's a criminal justice issue. It's also a public health issue. It is a significant cause of death for young men, particularly, for example, for young African-American men. And because this is such a key issue, actually, I've worked quite a lot on this issue since about 2015. In past work, we focused on creating and analyzing a national traffic stop data set, tracking stops all across the United States. We worked as journalists who submitted data requests to more than 150 police departments over the course of 5 years to try and pull in all that disparate data from all those different sources. This was really a huge amount of work on their part. We then wrote tens of thousands of lines of code to try and put that data into a standardized format. And we put all that data online, and I encourage you to check it out. It's become quite a widely used resource for studying policing. If this is of interest to you, and you can just click on this link and download the data immediately. We also analyzed that data for evidence of bias in the stop decision, search decision, and the effect of policy changes like the legalization of marijuana. In the course of doing that, we also developed more general methods for trying to quantify bias in policing. Those methods were used by journalists, including the Los Angeles Times, to document sort of a bias against Black and Hispanic drivers. And in response to the work that the journalists did using our methods, the LA Police Department, in fact, announced that they would reduce random vehicle stops. So this was a case where sort of the data science methods resulted in concrete changes to policing policies. And so policing is a topic which has been close to my heart and a topic of significant work for a long time. Today, I want to talk to you about two relatively new pieces of work that I've done here in collaboration with some wonderful collaborators. The first is around using racial inconsistency, and I'll explain what I mean by that, to develop a new statistical test for bias in policing and more broadly. And the second is around using dashcam data to measure disparities in policing. So let's jump right into it. This is a working paper. It's extremely new work. This has been online for 23 hours and 37 minutes. So your comments are extremely welcome. This is like the first time I've given an external talk on this. And it's joint work led by Nora Guerra, who's a PhD student at Cornell, who's really done a wonderful job on this. The title of the paper is Testing for Racial Bias Using Inconsistent Perceptions of Race. So just a brief primer on how we traditionally test for racial bias. What do we do? Conceptually, no math here. We take two people of different races and we compare how they're treated. The running example, what we're going to study throughout this part of the talk is, are Hispanic drivers more likely to be searched after the police stop them than are white drivers in a racially biased way? And so, we compare, for example, Hispanic drivers to white drivers. We say, Hispanic drivers are searched 4% of the time, white drivers are only searched 3% of the time. This could be indicative of racial bias. Of course, the immediate response you get is like, well, maybe there's some difference between these groups of people besides their race. So what we typically do then is we attempt to control for all the different possible confounding factors, like when the, stop occurred and where the stop occurred and what the driver was doing and a billion other things. And then if we can control for all those things, then we can attribute the remaining differences to bias. We can say these two people were sort of equivalent on all the things that should matter to whether they were searched, except for their race. If one race group is more likely to be searched, this is attributable to bias. Okay, but this sounds much easier to do than it actually is, right? And the reason is that dealing with these confounds, these things that separate people of different race groups, is really, really hard. Two people typically differ in myriad ways. Their race is only one of those ways. And it's really hard to control for all the other ways in which they might be different and thereby convince people that in fact these differences are attributable to race, as opposed to one of the gajillion other ways they might be different. And to make this problem worse, typically all the ways in which two people can differ are not written down in your data, right? So like plausibly, right, we might want to control for how suspicious is the driver acting, because that might be a legitimate reason the police decide to search them. But no policing data set has a measure of like driver was acting suspicious on a scale of 1 to 10. And so you can't control for this thing. So how do people try and deal with these problems? Long literature, going back decades. Not going to talk about it in huge detail now. Sometimes people try to run randomized controlled experiments, right? You may be familiar with the experiment that, sent identical resumes, except some had names that were sort of more associated with Black applicants versus white applicants. And then they just, the resumes were identical, except for the fact that they randomized the name, and they found higher callback rates for the resumes with white names. Sometimes you can't run experiments. For example, in policing, you typically can never run an experiment. So instead, you might try and look for a natural experiment, something where something happened in the world that was as if you ran a random experiment. Sometimes you can't do either of those things, so you just try and do your best controlling for confounds. Long literature here. Okay, but all of these things are trying to basically say, let's compare two different people of different races, and then we're going to try and remove and control confounding factors so that we can attribute the remaining differences to bias. That isn't what we do here. We do something fundamentally different. Rather than comparing two different people of different races, a Hispanic driver and a white driver, we instead study the same person over time. Now, your immediate reaction to this might be like, what? That doesn't make any sense. Like, each person has one race. This race stays constant over time. So if you study the same person over time, there's no racial variation with which to try and get a racial bias at all. This doesn't even make any sense. But that's actually not true. Race is not, in fact, constant over time. What do I mean by this? Well, in particular, perceived race, how your race is perceived, a wealth of social science literature has shown is not, in fact, static over time. According to constructivist theories of race, which have a lot of evidentiary support from a long line of literature in sociology and many other fields, observers rely on context and racial cues in order to perceive someone's race. And these cues can vary, over time. And this creates inconsistency in how someone's race is perceived over time. A famous example of this is, for example, if you show people identical faces, but one of the faces, the person is wearing a suit and one of them is wearing sort of janitorial attire, then for people at sort of intermediate skin tones where it might be ambiguous, are they white or are they black, people are more likely to be perceived as white when they're wearing business attire rather than janitorial attire. So this is like one of many examples. Clothing is one of many things that can influence how race is perceived. All this means that perceived race is not, in fact, constant over time. So what do we do? Specifically, we test, is the same person treated differently when their race is perceived differently? And in our specific setting, we look at, is the same person more likely to be searched by police when they are perceived as Hispanic than when they are perceived as white? And if they are, this suggests anti-Hispanic bias. Now, this seems sort of intuitive, right? But we actually go into the weeds a little bit to think about like, why does this actually suggest bias? And in particular, we motivate our test with a model that was proposed a couple of years ago. And here's how the model works. If you don't understand all the details here, that's fine. I think the rest of the talk should still make sense. The model assumes that when the officer stops the driver, they observe features X about the driver. Lots of information about the driver. That might not be something that we as the analyst observe, but it's what the officer observes. That could include, the date and time of the stop, how nervous the driver is acting, what kind of car they're driving, et cetera, et cetera. On the basis of all these features, the officer perceives the driver's race. And we're going to assume that's some number that ranges from 0 to 1, with Hispanic being 1. For simplicity, I describe this in the context of a binary race variable, but this approach is applicable to multiple racial categories as well. So after perceiving the driver's race, the officer then infers the probability the driver is carrying contraband. So like they're carrying, drugs, weapons, et cetera, things they're not supposed to be carrying. And they search the driver if this probability exceeds a threshold. So for example, the officer might infer there's a 40% probability the driver is carrying contraband, and their search threshold is 50%, and so they don't search the driver. And maybe, if their search threshold were 30%, they would search the driver. Now, the model allows both that probability and the search threshold to vary by race and by other factors. And I should say this is like a pretty standard way that people tend to model police searches. This is not novel. So, okay. So if we observe that the same driver is more likely to be searched when they are perceived as Hispanic, 3 possibilities might explain this under our model. Let's talk through them. The first possibility is that basically the police infer that the same person is more likely to be carrying contraband when they perceive the driver as Hispanic. So if they perceive you as Hispanic, they infer it's more likely that you're carrying contraband, and so they're more likely to search you. This is illegal. It's known as statistical racial discrimination. You're not allowed to do it in police searches. The officer is not allowed to say, oh, I searched you because you were Hispanic, and so I inferred you had a higher probability of carrying contraband. You're not allowed to do that. So that's straightforward bias. A second possibility is that the police apply a lower search threshold when they perceive the driver as Hispanic. So they say, oh, if you're white, I'm only going to search you if you have a 50% probability of carrying contraband. If you're Hispanic, I'm going to search you if you have a 10% probability of carrying contraband. This is also straightforwardly illegal. It's known as taste-based racial discrimination. It's, what people sort of mean a lot of the time when they say discrimination, like you're not allowed to apply different thresholds to people on the basis of their race. The third possibility is a bit more complicated. It's that there's some aspect of X, of those other things, those other factors that affect search probability or contraband probability and threshold that change for the same person over time. And this thing that varies over time affects both their perceived race and the officer's search behavior. Now, this requires further investigation because it's possible that some X don't suggest bias. Let me give you an example of something that doesn't. Imagine, this is purely hypothetical, that the same driver interacts with both Hispanic and white police officers. And Hispanic officers are both likelier to perceive a driver as Hispanic, and they're also likelier to conduct a search. So even if no individual officer is biased, even if every officer individually treats both, people the same, regardless of their perceived race, you're still going to see this effect where people are more likely to be searched when they're perceived as Hispanic, but it's an officer effect. It has nothing to do with how the individual officers are treating people. Okay, so you might be like, okay, well, you told me that the whole problem was controlling for confounds. Now you've told me there still might be confounds. Have we actually made any progress at all? It actually turns out that we have made some progress. And the reason is that, traditionally, when we compare 2 different drivers, we have to control for everything which could legitimately affect the search decision, right? So, it could be everything from date and time and how nervous the driver is acting, and many of those things won't be observed. In contrast, here, we have to control for a much more limited set of factors. Specifically, they have to satisfy 4 criteria. They have to affect the perceived race, they have to affect the search decision, they have to vary for the same person over time, and they have to not be clear markers of bias themselves. So for example, perceived skin color might vary over time, might affect perceived race, might affect the search decision, but if you're like, oh, I was just searching you because you had darker skin, no, that is not a legitimate justification for a search. Okay. So it turns out that this is a much more limited set of variables that you might have to control for, and we explicitly do check for whether those might explain our results. Okay, how do we actually test for this empirically? I'm not going to describe this in great detail now. Happy to go through in more detail if folks are curious. Basically, you fit a fixed effects to model. This is a pretty standard way to do it, but the point of the model is it's saying, is the same person more likely to be searched when they're perceived as Hispanic as opposed to as white? How do we actually fit this model? Well, we use open policing data, that same data set I was telling you about at the beginning, actually, from Arizona and Colorado and Texas. The reason we use these three states is because they're the ones who provide the data which you need to link the same driver across multiple stops, which we have to be able to do, right, to study inconsistencies in perceived race. So for example, in Colorado, we link the same person across multiple stops using their name and date of birth. And we look at whether searches and arrests vary depending on the perceived race of the driver. Okay, so when we look at the data, the first thing you might say in the data is like, can you even do this at all? Is there even any inconsistency in perceived race at all? So about 17% of drivers across all three states are stopped multiple times. And if you look at these people who are stopped multiple times, they have their race inconsistently perceived about 9% of the time. So this does happen, that someone's race is inconsistently perceived. And if you look at those folks who have the inconsistently perceived race, about 75% of them are recorded as Hispanic and white, as opposed to other combinations. So, Asian and Black or something like this. Consequently, we focus on our analysis on those group, which amounts to about 54,000 drivers, 157,000 stops. There's no reason in principle you couldn't repeat this analysis with other combinations of race groups, as long as you had enough data on them to actually be able to get, not super noisy results. So importantly, one really simple thing you could do, right? You'll always start by doing the simple thing. Don't start by fitting as fancy models. Is you can just say like, what's the search rate for this group of Hispanic white drivers when they're perceived as Hispanic versus white? And when you do this, you see that it's higher in all three states for when they're perceived as Hispanic. These numbers on their own, no confidence intervals, no statistical significance testing, so you can't really, interpret them too well on their own. So then we actually fit, our fixed effect regression model. And so what I'm plotting for you at the top is basically how much likelier does the model infer people are, the same person is, to be searched when they're perceived as Hispanic versus white. So you can see that the model is inferring that they're more likely to be searched when they're perceived as Hispanic. And that, again, this is for the same person, so it's sort of controlling for the person. And that difference is highly statistically significant. Now you might say like, oh, 0.4%, like, does that really matter? Yeah, it does matter because the thing about searches is people are pretty unlikely to be searched. So 0.4% difference in search rate is a really substantial fraction of searches. It amounts to about 24% of the overall search rate. Now, as I mentioned, the key thing here is like, does this persist when you control for things? And so we look at, does it persist when you control for the limited set of compounds that it's really important you control for? And it turns out that it does. Basically, I can talk more about why we included these specific things, but we included all of them because they were either used in past work or because they plausibly influence both how someone's race is perceived and whether they are searched. And so as such, we control for all of them. The point is that the finding of bias remains robust to controlling for all those things. It also remains robust when you control for a bunch of other things. Another question you might have is like, well, maybe when the officer searches someone, they spend more time with them. This is in fact true. And this gives them the ability to perceive their race differently. So for example, perhaps, and again, this is purely hypothetical, officers by default assume people are white. And then when they have the ability to spend more time with them, they can perceive their race more accurately. This changes their racial perception. And so maybe, it's really like a longer stops phenomenon. In order to check for whether this might explain the results, we test what happens when you control for how long the stop lasts, and results remain similar. So it doesn't appear to be a longer stop thing. We also, confirm that the results remain similar when you use alternate statistical models, basically like logistic regression rather than linear regression. And we also show that you see similar results if you look at arrests rather than searches. So this appears to be a pretty robust finding across statistical models, across controls, across outcomes. Some important things to keep in mind when applying this test. So so the basic conclusion is we find evidence of bias against Hispanic drivers in police searches in these states and also in arrests. More broadly, this test is applicable to tests for bias in other domains. Here are some important things to keep in mind when you do it. One is that you need data on perceived race, not self-identified race. We actually confirm this in our setting by reaching out to police departments in all three states who are quite helpful in confirming that. You're analyzing a subset of the population. Here we're analyzing bias amongst the subset of the population perceived as both white and Hispanic. And it's not clear, for example, that these results would generalize to Asian drivers. Another thing, and perhaps I won't go into these details now, although it is quite interesting, is you might ask, like, are the police like deliberately misreporting race, for example, to make, to try and conceal evidence of racial bias? there is evidence that this has happened from past work, including our own. That should not explain our results. And if anything, it would cause us to underestimate the size of the effect, because they would tend to sort of report people as white when they were searching them rather than as Hispanic. Okay. So to conclude, we find evidence of racial bias in the stop setting. More broadly, our test can be applied to assess bias in settings where two things hold. So if you have data sets where this is true, this is potentially maybe of interest to you. First, you have to observe the same person multiple times. And second, you need some measure of race data or perhaps other identity data like gender data, where it's perceived as opposed to self-reported. Right. So feel free to reach out or raise possibilities if you have ideas for such settings. All right. I'll just say briefly that I think this happens a lot. We found a bunch of other settings where one could potentially apply these methods. All right, let me tell you briefly about the second story. For those who thought that was like a little too old school and a lot of econometric methods, I promise this will make use of modern machine learning methods. So if you like those better, this is for you. This is joint work led by Matt Franke and with JD Zamfrescu Pereira and then with Wendy Ju, and it's published in fact last year. It's about detecting disparities in police deployments using dashcam data. So what do I mean by police deployments? This is basically like how heavily policed are different areas. How many police officers are there in different blocks and neighborhoods in New York City? Why do we care about this? Because it's an important way to quantify over policing. It can also result in downstream bias in algorithms, right? Because if some areas are more heavily policed, then you may tend to get more arrests there for the same level of crimes. And algorithms, which can be trained on arrest data, may sort of overestimate how risky these areas really are. But in spite of the fact that police data is really important, deployment data is really important, the police have been historically very resistant to releasing this. The New York Times has had sort of a series of battles with them. They don't even, it's totally understandable. They wouldn't want to tell you exactly where every police officer is, very reasonable. But they don't even really want to release aggregated deployment data with, in other words, how many officers are there in different neighborhoods? And that's a little harder to understand. So we decided to do the natural thing, which of course one would do, which is, find police, namely, basically take a data set of 25 million public street scenes throughout New York City and try to find all the police cars using AI. Okay. So, the image at right gives a sense of our data set. This is a map of New York, and it tells you sort of the number of images you have per census block group. And the point is, this is quite a big data set. The coverage varies across New York, but it's a ton of images. So you have pretty good coverage, although varying levels of coverage across different areas. Okay, so we're going to take this data set. We're going to train a model to detect police cars from the dashcam images. Maybe I should just say a little bit more about how this data is collected, by the way. Basically, it comes from, rideshare drivers like Lyft drivers driving around. And some of these drivers have cameras on their front dashboards, and those take pictures of things. There are obviously like creepy or bad things you could do with this data, but we decide to, use it to keep an eye on the police and stuff. Okay. So we're going to try and estimate the probability that residents of a given group, for example, Asian residents, have a police vehicle visible when they're on a street in their home neighborhood. There are a couple biases in this data set that's important to compensate for in order to get an accurate estimate here. The first bias you might have already guessed is that like the locations in this data set are non-representative. Like we have a lot more pictures in Manhattan than we do in other boroughs. And so to deal with this problem, we have to reweight the distribution to match the population distribution. Happy to give more details on how we do all this, by the way, if it's of interest. A second issue you might have is like, your classifier, the thing that detects police cars from images, is not going to be perfect. And so you need some way of sort of compensating for that imperfection. And so what we do is we actually estimate how imperfect the classifier is, and we show that it doesn't vary too much across different areas of New York, which could also introduce bias to your estimates. There are some biases we can't compensate for, and I'll return to those at the end of the talk. Okay. So what do we see? Well, here this shows you some dash cam pictures, and the purple boxes are our detections, and you can see that like the classifier does a pretty good job. Maybe you don't just want to see 4 examples of this. Like maybe these are cherry-picked examples. These aren't cherry-picked examples. The model actually does quite well. So it has an AUC of 0.99, which those of you who worked with AUCs, that's quite a high AUC. 1 being the maximum value. Similarly, the average precision is quite good as well. And so we have this, model that appears to identify cars quite accurately. we apply it to try and estimate sort of spatial and demographic disparities in policing levels. And this shows our inferred spatial disparities. You can see that like the model sees a lot of variation in policing levels. Like Manhattan and particular regions of Manhattan are much more heavily policed than, for example, Staten Island, which is this island down here. Spatial disparities on their own maybe aren't that worrisome. Like it kind of makes sense that there might be a lot of police in Times Square or whatever. More worrisome, though, is that we see substantial demographic disparities. Okay, so this is just sort of summarizing the spatial disparities I just showed you, where sort of Manhattan faces higher policing levels. But we also see racial disparities in how heavily different areas are policed. For example, Black and Hispanic residential neighborhoods have higher police deployment levels than do white and Asian residential neighborhoods. We also see that lower income neighborhoods face higher policing levels than higher income residential neighborhoods. In general, the picture of policing we see arising here is quite complex. And you know, part of this is what I would call the Hudson Yards Rikers Island effect. So I don't know if you've ever been to Hudson Yards in New York. I don't necessarily recommend a visit if you haven't. It's like this weird, like incredibly bougie shopping mall with like golden lights and whatever. And that's one of the areas with sort of the highest levels of policing, because it's it's like this very it's just like heavily policed, sort of sterile feeling area. On the other hand, we also see very high policing levels in Rikers Island, which is a prison. And so, these are very, very, very different places, but also, they are alike in that they both see high policing levels. I mentioned that there are some biases that this method can't compensate for. Here, too, I think is worthy of note. One is that we detect police cars. Of course, not all police are in detectable cars. They might be in unmarked cars. They might be on foot. We can't detect things like that. A second bias we can't compensate for is like images within each census area might be non-representative. So like, for example, if there's like a protest and the whole area around the protest is walled off to traffic, then we're not going to get any pictures near there. So even if there are a ton of police there, we're not going to have them in our data set at all, and we're not going to be able to detect that. So to conclude, I think one thing this work really highlights is the importance of getting better policing data. I think we find pretty convincing evidence of disparities here. And I want to be clear, by the way, that we're not concluding on its own that these disparities are in indications of bias. They could be indications of bias, but I don't think we have enough from this analysis to conclude that. What we do think, though, is that there's real evidence of disparities here, and that the public has a right to know about them. But it's not realistic to expect the public to exert oversight over police by like detecting 233,000 police cars from 25 million images. So we think it's really important that the police should just release aggregated deployment data to let us get better insight into these disparities that we find evidence of, and save us all a lot of time. This work has also had some broader impact. It's garnered attention from news outlets in New York City, and we also got some interest from the Brooklyn Public Defender Services, who are interested in disparities in mass surveillance conducted by the police. I should mention there's a lot of other stuff you can detect from dashcam data. And I think some of this has substantial public upsides. One thing Matt is currently working on is, can we use this to detect street flooding? Here, shows some representative images of where New York was flooded last year, and you can indeed see this from the police car data. And so, we're hoping to release a paper on that in the next few months. All right, thanks very much to you for your attention, to all my collaborators in particular.